Now, with ionic compounds, it's really obvious what is being oxidized, what is being reduced, as a result of our ability to follow the bouncing charges. With organic compounds, though, everything is bound covalently, so it tends to be a little harder to notice. What we want to ask ourselves in organic chemistry, which is mostly built from carbon, hydrogen, and oxygen with smatterings of other elements, is in which of these bonds does the carbon have more ownership of its electrons? Because if I go from a bond where the carbon is dominating that relationship, it's really holding on to the electrons 70% of the time, or 90% of the time, or even 50% of the time, and then a reaction causes it to no longer have control of the electrons that same way, I could also consider that to be an oxidation. I could consider that to be a loss of its electrons. So based on electronegativity, which I'll remind you here, carbon 2.5, hydrogen 2.1, and oxygen 3.5. As I make these three bonds, which are varying degrees potentially of polar or nonpolar, which one of them would have the left-hand carbon owning the electrons the most? Pause the video, think it over, and come on back when you're ready to hear the answer. All right, well, if we look at these here, since carbon has this 2.5 electronegativity, which is locked in, but hydrogen here is 2.1, even though I consider this generally a nonpolar bond, if either atom is going to claim more ownership of the electrons, it's going to be the carbon. Doesn't really have a dipole. I'm going to kind of put this in quotes almost, but whatever it would have is like that. On the other hand, over here with the oxygen, electronegativity of 3.5, remember that is a legit dipole pointing this way. Lastly, the carbon-carbon bond is going to be purely nonpolar covalent. So I would say here that the carbon has the most ownership of the electrons when it's in a CH bond, because it does have a little extra pull. It might only be 60% to 40% in terms of the time that the bonding electrons spend around each atom, but that's enough to say this one beats out this one, which is 50-50, and this one, which is substantially less than 50-50. So we'd say the carbon-hydrogen bond, most ownership of the electrons for that carbon on the left, and over here, the least ownership. So this means that anytime I add hydrogens to a molecule where they weren't originally bound to a carbon, I'm going to give the carbon more ownership of its electrons. Remind me, which organic reaction did that? Okay, I hope what you're yelling at your screen right now is hydrogenation. When you hydrogenate a double bond, remember, you broke a CC bond and you tacked an H on in its place. So now a pair of electrons that were being shared 50-50, maybe they're being shared a little more like 60-40 or 70-30 between these two atoms, and this carbon's winning. If that is a reaction that gives the carbon more ownership of its electrons, we're going to call that a reduction reaction. Gain electrons, and as a matter of fact, gain H. While we're at it, that means that removing hydrogens would do the opposite. Removing hydrogens is going to always give the carbon less ownership over its electrons, and the reaction that did that in our organic reactions discussion was dehydrogenation. And so the other name we'll have for dehydrogenation is oxidation. Most of the time, in an organic context, that is what we mean when we say we oxidize something. It means we pulled off two H's. And so what we might be doing is pulling off two H's and making a new CC bond. Or, for that matter, pulling off two H's and making a new CO bond. Remember the way we made carbonyls beforehand. Either of those are going to deprive the carbon of its electrons, and so we're losing E-. And of course, that is also going to be seen by a loss of H. So now that we've established how these two bonds swapping back and forth can be considered oxidation or reduction, let's not leave out the formation of a CO bond. That is another way to definitely give ourselves less ownership of the electrons for the carbon. And so forming CO bonds can do it too. But there's really only one functional group we've studied that is usually oxidized that way, and it's the aldehyde. An aldehyde, remember, starts off with an R group attached to a carbonyl with an H on the end of it. The way that aldehydes are generally oxidized is to pop off that H and put an O in between these two. And so we wind up with this as our new structure. Notice there will still be an O to H bond. That O is going to be owning that H's electrons too. But in particular, we go from a CH bond that did have the carbon winning the tug of war a little bit to a CO bond in which it is decisively losing it. Remind me, what do we call this product functional group? Okay, I hope what you're yelling at your screen right now is carboxylic acids. And if you notice, just like we saw here with the hydrogenation and the dehydrogenation being opposing processes, if one of them is oxidation, the other one has to be reduction, well, the same thing will be true here. Carboxylic acids will be reduced by undergoing this change right here, losing their oxygen and having the H reattached in that spot. They are the only functional group we're studying right now that undergoes reduction in this way. Now, particularly this reaction is going to be desperately important when we get to carbohydrate chemistry because it is the way that sugars act as reducing sugars. They undergo this reaction, they get oxidized, and as a result, something else, something visible to us, gets reduced. Look forward to that after this upcoming test. So to finish things up, what we've seen here is that oxidation can involve the loss of electrons, or I should say it always involves the loss of electrons. It's just not always obvious that that's happened when you look at something. It can involve the loss of H's, usually 2 of them at a time. And it can involve the gain of O, which, interestingly enough, sounds more like oxidation than anything else we've talked about so far. Meanwhile, reduction can involve the gain of electrons, it can involve the gain of 2 H atoms, or it can involve the loss of O. But again, remembering that these two right here are pretty particular to this reaction, the oxidation of aldehydes and the reduction of carboxylic acids. I do want to point out then that one of the other reactions we've talked about, hydration, ends up not being redox. Because if you think about hydration, you're going to take what was a CC double bond and you're going to add to it an H on one side and an OH on the other. So what you're essentially doing is making a CH bond, so you've gained H's, but you're also making a CO bond, so you've gained an O. And so those two are going to cancel each other out, and as a result, hydration is not going to be considered a redox reaction. After you've done some practice questions on these reactions, but before you jump into the videos on energy and equilibrium and kinetics, make sure that you've actually done the bottom of this page that asks you to remind yourself of some of the things that we learned in week 5 that we're going to be applying here. And also on the next page, do the brainstorm. Take 5 minutes and just think over the answers to some of these questions just from your daily life. We're going to take your intuition and try to apply it to what we see in this very theoretical landscape. See you there.